Welcome into quadratic surfaces, and this is just going to be a very short introduction. Now we talked about lines, we've talked about planes which are degree 1, now we're taking up to degree 2, so we're dealing with quadratic surfaces, and we have a long equation that we're going to write that's going to generalize quadratic surfaces. So bear with me. Ax squared plus by squared plus cz squared plus dxy plus let's just do xz plus fyz, maybe you can see where this is going, plus hx plus iy plus jz is equal to 0. Right, so this is our long quadratic surface equation. Now, again, we're going to see examples where this looks way more complicated than it really is. So just try to not get scared by this long equation. A through J here are all just coefficients or real numbers for our class. Okay, and I'm going to do a brief example. Now, it's an example you've seen before, in which there's a bunch of specific quadratic surfaces that we'll talk about in the preceding parts of this video. But the first one that I want to start with is a very easy case of, and I'll leave some space here. We have x squared over a squared plus y squared over b squared. And we're going to say it's equal to some value here. We'll just call it r, right? So, or we'll say 1. We'll say 1, but it could be any number. You could say k, doesn't matter. Right, now what is this shape? Well, in 2 dimensions, right, so 2D, right, what is this? Well, this is an ellipse. And so the pattern you're going to see here, I know I've just done it with this shape, but imagine there's going to be times when it's only going to give you 2 variables, right? In this case, it gave us 2 variables. In 2 dimensions, we have an ellipse. But if we extend this same idea into 3 dimensions, right, so think about what's happening here. Our x and y are restricted, right, to this equation, but our z is a free variable that can run up and down and be whatever it wants. And so what we're going to end up with is a cylinder. And you can think of it like an elliptic cylinder, right, because in this xy plane we have an ellipse, but if z is free, right, you could think of the ellipse goes up and down, as you can see in this 3-dimensional figure here, right? So again, in the xy plane, we have an ellipse, right? And then if we just let z be free, right, you can imagine we have an ellipse, right? So you're in this elliptic elevator and it's going up and down, right? So now I've used this idea here, but there's other shapes that you could see. Right, so anytime, the main point of this is anytime there is a variable missing, it is considered what I call a free variable. It's allowed to travel wherever it wants, right? So essentially you end up going around that axis. In this case, right, we end up going around the z-axis because z can be whatever it wants. So just make sure we pay attention to these. Again, just a very brief intro into quadratic surfaces. Long equation, we're going to look at some specific ones moving forward in the next parts of this video. So I will see you there. Welcome into our first official quadratic surface. And the first one we're going to start talking about is the ellipsoid. Okay. Now with the ellipsoid, let's write the equation here. We have x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. Right, now this looks very familiar as far as it almost appears to be a sphere, but we have these different denominators here. Now all of these denominators, right, stand for, right, the a, the b, and the c all stand for the respective radius in that direction, right? So x is the radius in the x direction, so we'll just say radius in the x direction. B is the radius in the y direction, and C is the radius in the z direction, right? right? So even though it's a squared, b squared, c squared, right, we only want a, b, and c for the radius. Okay, now, if we don't want to memorize the equation and we want to break it down, right, so we can just visually see it, the best way to do it is to break it down into 3 two-dimensional images, and we call these images traces. Right, and essentially, we did this before, we're just going to look at each individual plane. And so let's say if we want to look at the xy plane, right, this is when z is equal to 0. And so, well, what happens? All we have to do is replace z with 0, and we'll see what we get. X squared over a squared plus y squared over b squared is equal to 1, right? That's what happens when we plug in 0. And what is this? Well, this is an ellipse, right? So in the xy plane, we have an ellipse. And we're going to repeat this process. Maybe some of you already see where this pattern is going, so feel free to speed through it. But if we're in the xz plane, right, this is when y is equal to 0. What does this mean? Well, this would be x squared over a squared plus z squared over c squared is equal to 1. And again, we have another ellipse, right? So we have an ellipse in the xy, we have an ellipse in the xz. Any guesses what we have in the yz plane? Right, so in the yz plane, same idea. This is when x is equal to 0. Plugging in 0 for x, we obtain y squared over b squared plus z squared over c squared is equal to 1. Right, and this is also an ellipse. Perfect. Right, so we have 3 ellipses. If we combine all those together, that's what we get is an ellipsoid. We have a 3-dimensional figure over here to show you. We'll do one quick example. Let's say we have x squared over, let's do 9, plus y squared over 36, plus z squared is equal to 1. Right, and really the only thing we need to identify here are the radiuses in each direction. Right, so in this case, right, a is equal to 3. Is the radius in the x direction, b is equal to 6, the radius in the y direction, and c is equal to 1, the radius in the z direction, right? So easy enough. We'll go through each one of these examples the same way. This idea of traces, breaking a 3-dimensional surface into 3 pictures in 2D is what we're going to use. So we should get familiar with this. This was a nice easy example to start with. I will see you in the next quadratic surface. All right, moving along, our next quadratic surface is a cone. And I'm going to write this equation 2 different ways, but we can agree that they are identical in their equivalence. All right, so one way we might see it, x squared over a squared plus y squared over b squared is equal to z squared. This is one possibility. Right? The other possibility is I might take this z squared and just move it to the other side and have it equal to 0. Right? Either way is fine. But just so we know, either of these is a very common way to see a cone written. Now, if we look at our 3D graph, notice it doesn't have to be the x in this place, the y in this place, the z in this place. Right, whatever essentially has the minus sign or whatever is equivalent to on this right side is what the cone will go around. Right, so you'll see in our 3-dimensional figure over here, the cone is going around the z-axis. Right, and what I want us to do is the same idea that we did last time. We're going to take this, we're going to break it into 3 two-dimensional images, and then we're going to see what we have. Right, so these are called the traces. And so we'll look at our xy plane. Right, this is when z is equal to 0. We'll look at our xz plane. This is when y is equal to 0. And we'll look at our yz. Ooh, squeaky. That's when x is equal to 0. So let's go ahead and do all 3. Right, we will have some 2-dimensional graphics pop up so we can visualize as well. If I plug z is equal to 0, this is maybe the most tricky one, or the trickiest one. What do we have here? X squared over a squared plus y squared over b squared is equal to 0. So maybe we need to think about, when is this true? Well, if I move the y squared to the other side of it, an x squared is equal to a negative y squared over their respective denominators, right? But the only way those two could ever be equal to each other, because x squared will always be positive, y squared will always be positive, a positive equaling a negative, it'll only happen at one number, right? So it'll only happen at a point, right? So our point here is 0, 0, 0, right? The z is already 0 because we're in our xy plane. We want to know when this left side will be equal to 0, and that can only occur when both x and y are 0, so we end up with just a point in our xy plane. Okay, so this is kind of the weird one here, but these two should follow pretty nicely. Right, let's see what we have. If y is equal to 0, that leaves us with x squared over a squared is equal to z squared over c squared. And you can imagine we square root both sides, but this simplifies to the absolute value of x is equal over a, over a is equal to the absolute value of z over c. Right, so we end up with this absolute value sign, and this is what creates that cone where it's crossing each other. Again, we should have an image there. Right, and same thing here, right? This will follow a similar pattern. When x is equal to 0, right, well, what happens is we're going to end up with the same exact thing, except y squared over b squared is equal to z squared over c squared. And again, this will be the absolute value of y over b will be equal to the absolute value of z over c. Right, so we have these absolute value signs here, and we have a point just in the xy plane. If we put both of those together, right, these are like crosses here, crosses there. We put all that together, we get a cone, right? But not like a typical ice cream cone where it's only going one way. It's going both ways, right? So one example, we'll draw that there. And we're just going to write some information about this. So let's say I have x squared over 4 plus y squared over, we'll just leave it at y squared, is equal to z squared over, we'll say 9. Okay, so again, you can think about these kind of like the radius in each respect, right? Because if we broke this down, right, well, what do we have? Well, we're going to have still a point, right? There's still a point in the xy plane. This will only be true, so this is still a point. In our xz plane, xz, right, we're going to end up with, and this is still at 0, 0, 0. In our xz plane, we're going to end up with these absolute value signs, right, where we're going to have x over 2 is equal to z over 3. Right, so it creates those crosses for the absolute value signs to form the actual cone itself. And same thing here, right, for yz. Same idea. We're going to end up with, well, this is just y is equal to still z over 3. Right, so again, we just want to know how to break this into 3 different two-dimensional images, just in case we don't want to remember this, then we can kind of construct it in our head as to what this should look like. Again, one talking point here is the fact that it's equal to z, or that it has the minus z squared here, right, tells us that the cone is going around the z-axis. If we interchange this, say we put a y over here, it'd be going around the y-axis, right? So pay attention to those details, and it will help us know the kind of placement in space of where this cone is. All right, I will see you in the next one. Let's go ahead and jump into our next quadratic surface, and we will be going over what's called, I'll try to spell this, oop, already misspelled it, hyperboloid. Ooh, hyperboloid. Okay, we'll go with it. Of one sheet. And now, one is special here because it'll be one piece. We will see one that has two in our next part of this video. But let's write down the equation. We're going to have x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. So notice this looks very familiar. The only difference is between this and a cone is that we have it equal to 1, right? So that is one of our differences. Okay. So let's jump into it. But also, last thing, before we do the traces, right, we're going to go do the traces. Again, the pattern remains the same here. Because this is a minus z squared, the hyperboloid of one sheet is going around the z-axis, right? So you can assume that anything that has the minus sign here, right, when it's a hyperboloid of one sheet, will be the axis that we're going to go around. Okay, so let's go ahead. We will do traces. And again, we're breaking this up into our 3 planes. We have our xy, which is when z is equal to 0. We have our xz, which is when y is equal to 0. And we also have our yz, when x is equal to 0. So let's see what happens in all 3 of these planes, and then we can kind of collaborate with all those images in our head and come up with our 3-dimensional image. Right, so in our xy plane, when z is equal to 0, we have x squared over a squared plus y squared, very squeaky today. Let's see if we can find the right side of the marker here, is equal to 1. There we go. And we need to know what this shape is. We saw it in our past surface. This is an ellipse. Awesome. Let's see if I can grab another marker here so it's not as slightly better. Okay. An ellipse, right? Let's do the same thing in our xz plane. We're going to introduce a new shape here. Maybe we've seen it before. This is when y is equal to 0. We have x squared over a squared minus z squared over c squared is equal to 1. So maybe we saw this way back when, or maybe we totally forgot about this shape. This is known as a hyperbola. Hyperbola. I think I got it. Right, and this is why it's called a hyperboloid of one sheet. And maybe you've already noticed, for our yz plane, we have the same, right? X is equal to 0. So we'll also, in our yz plane, it's going to be y squared over b squared minus z squared over c squared is equal to 1, which is also another hyperbola. Right, so one ellipse in the xy and 2 hyperbolas in the xz and yz. And again, all these can change, right? If this equation changes, right now we have a minus z squared here, but that could, right, if we switch the y and the z, right, notice how we'll switch our traces in the respective, right, planes. Okay? Right, so you could write this out. I give a brief example here just so we get a little bit, but again, the only thing that's really changing here are these a, b's, and c's, right? So let's say x squared plus y squared over 4 minus z squared over 9 is equal to 1. Right, so again, in our xy plane, we have this ellipse. And I won't go into too much details about the hyperbola. Right, so the ellipse here in our xy plane, and our radius, right, in our x direction is going to be 1. So let's just write this out. Radius equal to 1 in our x direction, and for our y, right, our radius will be equal to 2. Put an arrow. Equal to 2 in our y direction, right? And I'll let you guys go through the hyperboloid or hyperbolas maybe as an exercise to see what those look like. but we should have some graphs here as well, right? So hyperboloid of one sheet, next video, next part of this video will be hyperboloid of two sheets, and I will see you there. As promised, we'll follow up the hyperboloid of one sheet with the hyperboloid, and I'll spell it better, hyperboloid of two sheets, right? It has two pieces, and you'll see a visual over here. Now the equation goes for the hyperboloid of two sheets, negative x squared over a squared minus y squared over b squared plus z squared over c squared is equal to 1. So again, notice here the only thing that's switched between one sheet and two sheets are the signs, right? The signs have switched. Okay, so we're going to take this idea, you'll see the traces pop up here, and we're going to do the same thing, right? So let's look at, we'll write traces. We're looking at, we'll do blue as normal. So we'll look at the xy when z is equal to 0. We're going to look at the xz when y is equal to 0. And of course, right, yz when x is equal to 0. We'll get rid of the squeaky marker for a second, hopefully. Okay, so let's get into this. Let's set z equal to 0. What do we end up with? We have negative x squared over a squared minus y squared over b squared is equal to 1. And let's stare at this for a second. Right, is this ever going to be true? We know that x squared will always be positive with a negative sign in front. This will always be negative. And same thing here. This will be positive with a negative. This will be negative. Negative minus a negative. We can never get to 1. Even if we plug in 0, 0, right? We don't want 0 equal to 1. That's not true. So there's nothing hanging out in our xy plane. And you can see that from the 3D visual. There's nothing there, right? So, nothing. Right? There is nothing in our xy plane. Right, and that's why it's two sheets, right? So you see a gap there in between. Now our xz plane, what do we have? This should look familiar because we have, let's do negative x squared over a squared plus z squared over c squared is equal to 1. And this should look familiar from our last video. What is this? This is a hyperbola. I keep doing that. I put the B first. Hyperbola. There we go. Luckily, we're not in a spelling class. Made it worse. Okay, and same pattern here, right? YZ plane. What do we have? Well, essentially exactly the same thing. Negative y squared over b squared plus z squared over c squared is equal to 1. And again, we have another hyperbola, right? Did the same thing twice. A hyperbola. Getting ahead of myself. Right, so nothing in the xy plane as visually represented in our 3D image. XZ plane, we have a hyperbola. YZ plane, we have a hyperbola. And they will both be spelled correctly. Awesome. Right, I won't go into an example. I'll leave you with that. Again, we want to get used to this process of being able to break it down into 3 two-dimensional images. I know I keep repeating that. And also here, again, notice the pattern. Z squared is the only one that's positive. So guess what axis we're going around? We're going around the Z axis. Okay, I will see you in the next one. Let's keep it rolling. Our next one, right, only one more after this, is known as the elliptic paraboloid. And we should be able to look at this name and know, okay, elliptic, ellipse, paraboloid, parabola, right, should have some sort of combination. the equation we're going to go with is x squared over a squared plus y squared over b squared is equal to z over c, right? So I saved these for last because they're a little bit different. Notice here that there's no z squared over c squared, it's just z over c, but still the same pattern, right? Z is kind of isolated, so guess what axis it's going to go around? It'll be the z, right? So let's take this, we'll go over here, we'll do some traces. And we'll do the same thing, right? Our xy plane, we'll go through these one by one. Let's do z is equal to 0. I'm also going to talk about when z is some value here, right? Because I want to discuss that because it's good for this because, or else this elliptic part might not make sense. Xz when y is equal to 0. And of course, yz when x is equal to 0. Okay, so let's plug in 0. First things first, right? Well, what do we have, right? This should again look familiar. X squared over a squared plus y squared over b squared is equal to 0, right? We had this when we were doing the cone. The only time this is true is where? At a point, right? So I'm going to write, we'll write it over here. We'll say this is going to be a point, right, in just the xy plane. However, what I want us to do is also think about the example, put a little bit of a line here, when it has some sort of value, right? So think about if we took another cross section, right? This is what's happening. We're taking a cross section or cutting it right in that xy plane. We're looking at what's happening. Well, let's take another cross section that's not just when z is equal to 0. Let's say z has some value, and we'll just call it k. Right, so the question is, if we have this, and we'll just say z is going to be some value over c. So we'll just call this k. Right? K is just some random constant number, right? Divided by c. So it's fine. Right? Well, think about what this is. Well, this is the equation of an ellipse, right? So in our xy plane, you'll see this here. In our xy plane, we have a point, but if we start taking a cross section, so imagine we have this elliptic paraboloid and we take a chop at any point or any slice parallel to the xy plane, we're going to end up with, this is an ellipse, right? So there's a point in the xy plane, and then as we move up, take a chop anywhere through there, you'll end up with a ellipse, right? So I'll just write it in here. Right, so in this case, it is kind of necessary to make sense of this, right? This elliptic part is if we take a cut somewhere else or a cross section somewhere else. Okay, now in the xz plane, these end up being very nice, right? What do we have? We have x squared over a squared is equal to z over c. Ooh. And this ends up being fairly nice, right? What is this shape? Well, this is just going to be the second part here, a parabola. Gotta get non-squeaky markers. Parabola. And guess what's going to happen for our last one here, right? Same exact thing. X is equal to 0. Right? We have y squared over b squared is equal to z over c. And again, we end up with a parabola. Right? So thus an elliptic paraboloid, right? So, I mean, if you would like to, you can see it here, right? Essentially, right, we know what this shape is, an ellipse, right? And these are the radius in the respective directions. So A is the radius with the x direction, B the radius in the y direction of this ellipse in our xy plane, and again, a point when z is equal to 0. Here, if we have a parabola, just so we can move everything around, I'm going to look specifically at the xz, right, in which we have x squared over a squared is equal to z over c. And if we want to make it look a little bit more familiar, right, this indeed is just a parabola with z is equal to c over a squared. So some constant, right, times x squared. Right, so this constant will vary on how steep or how wide you could say our parabola is in that direction. Right, so one more to go. I will see you in the next one. Last quadratic surface, we are going over the most interesting one, hyperbolic paraboloid. Paraboloid. Let's see if I can get no misspells. Okay, now the equation for this is going to be, let's use a different color, hopefully a non-squeaky marker. We have x squared over a squared minus y squared over b squared is equal to z over c. So again, notice it's very similar to our elliptic paraboloid that we had before, except we've switched the sign of one of these. Right? It doesn't matter which one we switch, and again, it's equal to z, which means, z is kind of the standout here. But again, we can flip any of the variables to either side, and it would just be changing the orientation of the shape. Okay, so we'll take this, we have our three-dimensional shape. It looks a little funky. Let's see if we can break it down. We have traces. See if I write on the side of the marker, if it won't squeak. We'll do our x, y. Nope, that's not working, which z is equal to 0. We'll go back to blue. Let's do our x, z, in which y is equal to 0. And lastly, we'll do our yz. X is equal to 0. Okay. So our very first one in our xy plane should look familiar, because what happens if z is equal to 0 here? We end up with x squared over a squared minus y squared over b squared is equal to 0. Right, if we move some stuff around, if we move the y squared, b squared to the other side, and we simplify, we end up with these absolute values of x over a is equal to y over b. Right, so this is where we get that nice cross going on. You should see it in our 2D graph here. Right, so this is the interesting case, and you'll see the rest of these, should be fairly familiar. So now in our xz plane, y is equal to 0, so we're just plugging in 0 for y. What do we get? Well, we're going to get x squared over a squared is equal to z over c. And what do we have here? Well, we just went over this in our previous shape, thus the paraboloid. This is going to be an upward, and I'm mentioning upward because we might find something different in this one, facing parabola. So we'll just put upward parabola. Okay, and same thing down here, except notice we have a negative sign. So why did I put upward? Because, this will be a downward facing parabola. Okay, so again, we're looking at these in all these two-dimensional images. If we looked at our xz plane, we'd see an upward-facing parabola. If we looked in our yz plane, we'd see a downward-facing parabola. So again, we're just paying attention. Because x has the positive sign here, it is the upward parabola. Because y has the negative sign, it is the downward parabola. So it kind of looks like what we would think of as a saddle or a Pringle. If you look at it in different directions, there's going to be different upward or downward facing parabola. And if we look at it straight down into the xy plane, we kind of visualize, you could imagine like an X or a cross. Okay, so that is it for quadratic surfaces. I know we went through it fast. Please, again, get used to this format of traces and also cross sections. So again, I mentioned in the elliptic paraboloid, sometimes it's necessary to take a cross section that isn't necessarily when z is equal to 0. When we did that, we saw there was an ellipse in that cross section. But for this one, fairly straightforward, easy to utilize the traces and see the different visualizations. So Thanks guys, I'll see you in class.